All right, so this is the last topic that we have in this class that we're going to go over. And this is called Induction Proofs. So we're writing proofs for things, and proofs is something that you probably spend a lot of time talking about in your geometry class when you've looked at doing two-column proofs, you've done some paragraph proofs, thinking about like how to prove different geometric properties of shapes. And then in your algebra class and in this class, we've also done some proofs of things, like using the limit definition of the derivative to determine that the derivative of sine is cosine, or the derivative of e to the x is e to the x. And something common in all of those proofs has been kind of going through the step-by-step procedure of stating something and then saying it equals something else, so it follows that something else comes from that. It's a very analytical process. Usually that's called deductive reasoning and mathematical logic, right? We're using step-by-step procedures to show that every step along the way leads us to this final conclusion. So that's one way to prove things, but it's a very intensive way to prove things, and it's not always easy. Sometimes those proofs get really, really long, or sometimes you just need to know a lot of math to do it. Think about those limit definition proofs. And some of them get really complicated in how you have to manipulate different things in the equations or in that fraction for the slope that allows you to take the limit of it to find the derivative, stuff like that, where it does become pretty complicated. So this is a different way of doing things. This is called induction proofs, and it's with inductive reasoning. And what that means is really looking at patterns. It's following on from sequences and series. We looked at having these patterns, having this recursive aspect to something. Right? If something happens, you can know what the next thing is, and you can know what the next thing is. Like in a sequence, if I tell you I have a sequence of numbers that's 2, 5, 8, and I ask you what number comes next, well, you can look at, well, from 2 to 5, I had to add 3, from 5 to 8, I had to add 3, so next would be 11. That's using an inductive reasoning process. You're looking at a pattern and building up that pattern to think about what comes next. So we're going to use that sort of thinking to prove statements that would otherwise be really hard to prove. So let's think about this without some math for a little bit. So let's think about a line of dominoes. I'm going to draw out some dominoes. These are dominoes. And I have a whole row of them. And I want to prove that all the dominoes fall down. Well, right now, none of them are falling down. They're all standing up. So that doesn't help. But let's think about what we know about dominoes, the way they're set up in a row. I know that if I have one domino that falls, then the one right next to it will also fall, because this one will fall and knock the next one over. So any one of these, as long as one of them falls, so let's say this one falls, then that's going to knock this one over and this one's going to fall. And then this will knock this one over and this falls. And this knocks this one over and this falls. So I've kind of proved that a lot of them fall just by thinking that one will fall. But now I've proved that 4 of them fall, but not all 6. So how do I prove that all 6 fall? I need to say one more thing. I can't start at the third domino. I have to start at the first one. Right? So if I know that as long as one domino falls, the next one will fall, and the first one definitely falls, then it knocks the second one over, which knocks the third one over, which knocks the fourth one over, which knocks the fifth one over, which knocks the sixth one over. That's the process we're using. It's this pattern building process. We start off with our initial value, saying that that works, that fell, and then we know that as long as one falls, everything after it falls. So that's our non-math kind of logic on this. So let's think about how this works in a more math context. There's some mathy words for this. And it says that if S of k is true for some positive integer k, so if some statement is true for some number, then the next one, k plus 1 is also true. So that's what we did here. When if the one domino falls, the next one also falls. And then the first thing is true. The first domino falls. Usually you see these conditions written the other way around, but I find it easier to think about the logic in this order instead. So that's why I've written it like this. In the past, students have usually had trouble understanding it in like the regular order that you see written out in most textbooks. But this order seems to help more. So we'll try going through that. When you write proofs, generally, you want to have a strategy in place. Writing proofs is like writing an essay. It's making an argument. It's something you would do in any discipline. And so something that's common in all of that is that you need to be clear in your writing. You need clarity, you need organization, you need it to be convincing to the other person. So for us, we're going to label every step. So we're going to have that first thing. We're always going to start off with like, what are we trying to prove? So we'll say to prove, and then say something. Then we'll show, when we write the proof, we'll usually do it the other way around, but let's do it this way. So we're going to make something called an inductive hypothesis. And an inductive step. This is the bit that talks about as long as one domino falls, the next one falls. So let's write this in terms of the domino proof. So to prove, I would say all dominoes fall. All dominoes fall down. My inductive hypothesis, this is where I'm making an assumption. And I'm saying assume, or you can say suppose, one domino falls. Then we can show in the inductive step, then the domino next to it also falls. So that was that first bit that we did. The last thing is called the base case. This is where we show that the first domino falls. So base case, the first domino fell down. So now combining these three things together, we can say that every other domino falls down, because if the first one fell, and we know that as long as one falls, everything else then the one next to it falls, then if the first one fell, that means the second one fell. And if the second one fell, that means the third one fell. And if the third one fell, that means the fourth one fell, and so on. And so then the last thing will be a conclusion. It says, by induction, we showed that all dominoes fall down.